today is mostly going to be focusing on kind of introducing you to graphs and networks and how they can be used to create mathematical models to find the most efficient way of doing things. In most cases, that's what we're trying to do with these graphs and networks. So it's kind of like a model, a simplistic representation of something that is like a real network. And by simplifying and doing some maths on these models, we can often find, for example, the shortest way to get from A to B. So if you use Google Maps to try and go somewhere in traffic, it's using some clever maths to work out, okay, which series of roads and paths is going to help me get from A to B fastest. And we do that by taking a map, for example. So here I've got an example, I think it's some sort of like tube, it's a train map, and kind of simplifying it. So I just need to grab my pen. So simplifying it. Now, what we do is we have, for example, here we have some stations, and we call these stations, all of these kind of stations, these dots, we're going to call them nodes, or vertices. That would be singular node and vertex for just one of them. And then we've got the paths that kind of join up all of these nodes. These paths are going to be called arcs, or there's something else we call them down here, arcs or edges. And we can draw diagrams using these nodes and these arcs, etc., to break down a kind of a colourful map like this one into something that's a bit simpler that we can do some maths on. That in a nutshell is what this section is going to be all about, this section and the next section that we'll look at as well next week. So we want to, by the end of this lesson, know how graphs and networks can be used to create mathematical models, and also be familiar with some basic terminology used in graph theory. There are lots of kind of weird and funny words in this section of work that I'm going to introduce you to today, so that we can start to look at this thing called Dijkstra's algorithm. So you'll notice that the section in OneNote is called Dijkstra's algorithm. It's a way of finding the shortest path between two vertices in a network, but we'll come to that later. First, today I just wanted us to concentrate on familiarising with basic terminology and understanding what the graphs and networks are. So without further ado, I'm just going to talk through the notes. So please do make your own notes. Feel free to pause the video, make your own notes and so on as we go along. And yeah, let's see what we've got here. So what is a graph? So when we're talking about graph theory in maths, a graph is a collection of those vertices or nodes, points, that are connected by edges or arcs. If these edges have a number, it's called a weighted graph or a network. Now, if you think about the example I gave with Google Maps, different pieces of road will have different distances attached to them. And if I wanted to find the shortest distance from A to B, I'd want to take that distance into account. So these distances are what we call the weights of each arc. So it's giving a numerical value to those lines. That usually relates to a distance or a time or something we're trying to minimize. A subgraph is a part of the original graph. Its edges and vertices also belong in the original graph. So for this example, I draw a subgraph of this network containing 4 vertices and 3 edges. So it would just be a part of it. I'll think about that example in a second, but a subgraph in itself might just be, I'll just draw one down here as an example, just this bit A, B and D. Okay, A, B and D, 7, 6 and 4. So this is a subgraph of the main graph. It's just a small part of it that I've kind of taken and written separately. So that's what a subgraph is, if you see that written anywhere. Then we've got the order. We can also call this the degree. I wouldn't worry about valency, we don't usually use that word, but the order or degree of each vertex is the number of edges meeting at the vertex. So you can think of this, you know, it's a measure of kind of complexity in some ways of, you know, the network that we have. If you look at A, it's got 4 arcs coming off of it. So the order of A will be 4. C has 2 arcs coming off it. So the order of the vertex C is 2. And E, for example, just has 1 arc coming from it. So the order of E is going to be 1. Okay. Whether a vertex is odd or even is an important property. So you can see that A and C have an even order, so an even number of arcs going into them. This means that they are even. Whereas E, for example, has an order of 1, which is an odd number. So the E is an odd vertex. That will become important more in the next chapter we look at, not the chapter we're looking at this week. It's good to know. It says 2 edges can intersect, but this doesn't mean there's a vertex there. So here we've got some lines crossing, but there's no vertex in the middle. They're just paths that cross. So no vertex there. Okay, let's try and think about this example here. So yeah, a route across a graph is described using capital letters. So for example, B, C, D, A, E. This would describe the route where we start at B and we move around the graph to C. B to C. This isn't a very good example because I can't get directly to C from B. Okay, I'll write what I think this should be. Say I go from B to C via A. This route would be BAC, and then say I go from C to D next. Next letter will be D, and here we're going from A and then to E actually. So if I now go from D to A and then A to E over here. Okay, my route would be described by just this series of letters. They describe the order at which I'm visiting the vertices in the graph. Okay, draw a subgraph of this network containing 4 vertices and 3 edges. So I want to draw some kind of like part of this graph with 4 of the dots, 4 of A, B, C, D, or E, just 4 of those letters, and 3 edges. So which have 4 vertices and 3 edges? 1, 2, 3, 4. Yeah, I think this will work. So say I have A, and I've got C, and I've got E coming off of A, and let's just do B. Okay, you can see here that I've got 3 edges, 3 arcs. Edge and arc just means the same thing. And I've got 4 vertices, A, B, C and E. And this is just this part of the graph that I've got. I've just drawn a subgraph, so just part of that graph. I've just drawn it to the side there. Okay, so that is a bit of terminology for you on graphs. Okay, and now some graph terminology. Now I wouldn't worry about this too much. We won't see it a lot in this chapter, but it's just if these words come up, I kind of want you to know roughly what it's talking about. Now, the type of math we're doing when we're working with graphs, we're often trying to get from one place to another place, usually, like I said before, minimizing distance or time or something like this. So we're interested in sort of paths around the graph. And there are all these funny words that we use to describe different paths around the graph. So a walk, for example, is a route from one vertex to another. So say I wanted to go from P to S. A walk might be, I'm going to go from P to R, and then from R to U, and then up to T, and then from T to R again, and then to P again, and then to S again. That was just like a random example. So that path I just did was PRU, T, RPS. So in that order. And what I just drew out was that walk. So it's a route from P to S, and obviously I visited some other vertices along the way. A path, that is a walk where no vertex is visited more than once. So you'll notice that I visited R and P twice in the example I just gave. So in a path we wouldn't be able to do that. A path would be visiting the vertices only once. So that example, or an example of this might be starting at P and going to Q. And then from Q, I think I'll go to R. Feel like going to R from Q, and then from R I'm going to go to T. I should have rubbed that out from before, and then I'm going to go down to U, and then I'm going to stop because I feel like stopping there. And you see during that example I just went to some vertices, 5 of them, but I didn't go to any of them twice. So that is a path. A cycle is a path that ends where it started. So if I started at P, I'd have to end at P. So an example of that might be going from P to Q, and then from Q to T, and then from T to R, and then from R back to P. So how I describe that is P, Q, T, R, P in that order. That's the order in which I visited the vertices. And I ended where I started. That is a cycle. A Hamiltonian cycle is a special type of cycle. It visits all the vertices and it ends where it starts. So for this one, I think I know what I'm going to do for this one. So the idea is, and there'll be different ways of doing this, so if you want to pause and try and find some other walks past cycles, that's a great idea, because my ways won't be the only ways, but I'm just going to think on the fly here. So if I go from P to Q, I visited P and Q, and then I need to go to R, so I think I'll go to R next, and then I'm going to go to T, then I'm going to go to U, then I'm going to go to S, and then I'm going to go back to P. And this is what we call a Hamiltonian cycle, because I've visited all the vertices on my way around. I haven't visited any of them twice, and I've ended and started at the same place, which is P. That's a Hamiltonian cycle. So here we've got some more definitions. So we saw what a walk was before, so just from one vertex to another, and the route can repeat vertices and so on, doesn't matter too much. A trail is a walk where no edge is visited more than once. So in fact, if I look at the same diagram, I will see here that the trail would be R, to this one in red, R to T to U to S. That would be an example. R, T, U, S. I just want a route from one vertex to another with no repeated edges. Sorry, there should be an S there. Okay, an Eulerian circuit is a trail that ends where it started. So it's a walk with no edges visited more than once, so none of the arcs can be repeated, and we need to end where we started. So an example of this might be, I'll try a different colour now. Say I start at R again. If I start at R, I want to finish at R. And I think I'll go to T first. So as I said before, there's lots of different ways lots of different paths I could take. I'm just kind of going where the wind takes me. So R to T, and then let's go to U. So I'll just try and write this down. R, T, U, and then I think I'm going to go to S. I'm trying to get back to R, you see, without repeating any edges. And I don't need to visit all of the arcs actually, so I don't need to go up to Q. I could just go to P from here and then return to R. Okay, so you see here that's this circuit. I've started and finished at R, and I've not repeated any edges on my way around. Okay, some other definitions. Sorry, it's a lot of that today. A connected graph, it has a path between any two vertices. So in a connected graph, all the vertices are connected. So this would be an example of a connected graph. They're all kind of connected between each other. A loop is an edge that starts and ends at the same vertex. So this bit over here is a loop. This diagram over here is a graph that's not connected. So if you look at this, it's like looks like two separate lines or graphs. So there's no path between, for example, these two and these two. So this is not a connected graph because there are not arcs that allow us to get to all parts of the graph together. We'd need to kind of jump and start somewhere else to get to each part of the graph. It's still a graph, just it's not a connected graph. We're only really going to be looking at connected graphs in this section. A simple graph has a maximum of one edge between a pair of vertices and no loops. So as you can see here, there's just single lines coming off of all the vertices. So this is a simple graph. There's also no loops. A loop would look like this. We don't have any of those. Now over here you can see that there's two arcs coming off this vertex going to the same vertex. So this is not a simple graph because I have more than one path sort of sprouting off both of them. And yeah, there's no loops, but yeah, it's not a simple graph. Okay, and a directed graph, we will look at this, but not for a few weeks' time. A directed graph has direction associated with the edges, so it means I can only travel in one direction along the edge. Say you were looking at some kind of like map in Google Maps and it was a one-way street. We'd want to show that with a direction to show that traffic can't flow in both ways on the graph. So that's what those are used for. And it's called a directed graph. Just need to be familiar with that word for now. Special types of graph. So we've got something called a tree. It's a connected graph. So there's no parts of the graph that we can't reach. All the arcs are kind of joined up into one shape. And a spanning tree, that's a subgraph of a bigger graph that contains all the vertices of the original graph. Okay, so we have to decide whether it's a tree or not a tree. The first example here, we just want all the vertices to be connected, but we don't want any loops, so there should be no way to kind of form a cycle within the graph. So this one over here is a tree. All the vertices are joined up and there's no loops. Or there's no way of forming a cycle, is what I should say in there. It's not quite a loop, but there's no way of forming a cycle there. This one over here is also a tree because all the vertices are connected to each other, but there's no way I can form a cycle there. This one, however, is not a tree because I can form a cycle from this bit over here. So I could technically sort of like go around this part and form a cycle. So this would not be a tree. In order to make it a tree, I'd have to cut off this part perhaps, or cut off this arc. I'd have to remove some of the arcs so that there wasn't a cycle there. Okay, draw 3 different spanning trees for the graph on the right. Let's just see how much I've got left here. Okay, why don't you pause here and see if you can draw some spanning trees. Okay, so perhaps you've had a go at that. Let me show you what this means. So 3 different spanning trees. So I want a graph that's connected, with all the vertices connected, sorry, but with no cycles. So one example of this might be to go from A to D, and then to go from D up to B, and then I'll go to F, I think, and then I'll go up to E, and then from F I'll go down to G, and from D I'm going to go to C. Now this is a tree, it's like a subgraph of the original graph. If I just draw it on for you, I've just drawn the same graph, but I've left off these arcs. So I've left off the arc CG, I've left off the arc AC, AB and BE, so there are no cycles, and this is a tree that relates to the original graph. We can of course draw the tree in different ways by leaving off different arcs. So I could, for example, do a different one, and you can think of your own examples here as well. These aren't going to be the only ones, but say I go from A to B to E now. So I'm doing this bit, and then I think I'll go down to D from B, and then I think I'll just go from C and F from D, C and F, and you just want to avoid making a cycle. And yeah, let's just go from G is the only one I haven't sort of touched yet, so let's go down to G. This is a tree because it has no cycles in it. If I had drawn on this vertex, for example, I'm forming a cycle between E, B, D and F, so that would not be a tree. Okay, last one then, let's think of one more. I'm going to go from A to C to G to F to E, so A, C, G, F, E. Let's go to D over here, and let's go back from E to B. Yeah, so I've reached all of the vertices, all of them are on my graph, and I don't have any cycles. So make up your own ones. There are many different ways of drawing trees that relate to this original graph. Okay, very quickly, a complete graph is a graph where every vertex is connected to each other. They make some pretty shapes, but we're not going to dwell on that for too long, so don't worry about that question there. Just really thinking about definitions for today. Isomorphic graphs show the same information but may look different. So we could draw the tube map, for example, in different ways. The way you see the tube map kind of in the conventional maps obviously isn't exactly how it looks in real life. It's been simplified and sort of spread out to kind of make it more readable, to make it clearer to figure out your routes. So it might look more like this, with the lines being a bit bendy and curvy if we were drawing a more realistic map, and over here it's kind of been changed, but it's the same graph because the nodes are the same and the arcs between them are the same, it just takes a slightly different shape. So that's isomorphic graphs. Label the following graphs so that they are isomorphic to the following graph. So the idea here is that I can draw this graph in the purple box in different ways. I could draw the arcs in different directions and it would still be the same. So if I were to label, say, A and B, see they're coming together to meet at C. So I'm going to draw it like this, and then I want to have 3 arcs coming off of E. So I'll draw E there because it's got 1, 2, 3 coming off it. That must mean D must be here, and that makes sense because there's an arc going from C to D and one going from D to E, and then from E we're going from F to G. So this graph here is isomorphic to the one in the purple box, it just looks a little bit different because things have been orientated a bit differently in space. And over here, this is also an isomorphic graph. So here we've got A and B joining at C, and we said E was the one with having 3 arcs coming off of it. So E's up here, D's here, F's here, and G's here. And if you look at the path between the vertices, they're all exactly the same. They've just been drawn at different angles and in different places, but it's the same graph. So you can check if 2 graphs are isomorphic by verifying that the corresponding vertices are connected to the correct corresponding vertices. Okay, we're going to leave it there for today. That's already quite a lot of new information. So what I'd like you to do now is follow the instructions, on lesson 15th of April. But you can try question 1 and question 2 from exercise 2A, and you can also try question 1 and question 2 from exercise 2C. And if you finish those, you can look at the rest of the exercise, but just focus on getting the first 2 done from each exercise. That would be fantastic. Any questions, let me know on Teams, and I'll hope to see you on Thursday.